All right, welcome everybody. Thank you for braving the winter weather here today. Uh, Kind of an interesting day. We talk about work today. So when I say work, I mean like the scientific work from physics. So oftentimes when we're thinking of work, we're thinking of a force times a distance. In a lot of cases, the force is the force of gravity, and the distance is like the vertical distance that we're lifting something up. And so, yeah, I mean, how does work relate to integration? Because why in the world are we talking about work in a calculus context is kind of a reasonable question. And yeah, the basic idea here is if you're lifting something, I mean, hey, if I was even lifting like this backpack off the ground, technically the bits of the backpack that like if I take this backpack, maybe let me set it here on the ground where it's like more flat, uh, and I lift it up, right? Some of the backpack here has been lifted further off the ground than other aspects of the backpack. And so if it all was sitting on the ground initially, and now this bit of backpack has been lifted however high it is, and this bit of backpack has been lifted not as high, that would affect the work computation. And so the integral is going to come into play when we actually take objects and slice them up to use integrals to compute work. And so after we see what we see today, you could ask yourself the question, hey, if definite integrals can compute physical things like work, could they compute other physical things? And the answer is definitely yes. Crack open any 300, 400 level physics or engineering textbook, and you are going to see integrals littered throughout them because integrals do the computations when you are summing up a bunch of things. Those things can be work, those things can be other things. So when it comes to work, let's just get the fundamentals down. Work is force times distance. The force is usually the force of gravity, and the distance is usually the distance that you are working against the force of gravity to lift the object. Now, force of gravity, or just in general force, Newton's second law, mass times acceleration. But when you think about the acceleration in the case of overcoming gravity, it's the acceleration due to gravity. I believe in your physics classes, you might approximate that with 9.81 meters per second squared. Here, whether it be on WebAssign or what we sort of provide on a quiz or something, is 9.8 meters per second squared. This will be provided to you, by the way. But yeah, so you got your 9.8 meters per second squared of acceleration. Whatever the mass of your object is gives you the force of gravity or the weight of that object. And then you take the weight and you multiply by the distance that the object has been lifted, and you would get the corresponding work. So why integrals, right? Like the idea of lifting the backpack off of the ground where certain amounts of the backpack have been lifted certain different distances. Imagine, it's a contrived example, but just imagine you had a cone-shaped tank full of water. Now, the parts of the cone that are nearer to the spout are lifted less in distance than the parts of the cone that are further from the spout. The parts of the cone that are down here at the bottom, there's a huge distance, where the parts at the top, there's just a small distance to lift it out. Now, since work is a function of distance, there's going to be different work on different portions of this cone of water. In fact, if you're breaking it down by the distances that things are being lifted, you would probably take slices of this water, taking like round slices horizontally. Essentially, you take disc-like shaped slices. And if you broke down the entire cone into a bunch of discs, in principle, you could compute the work associated with lifting that disc of water out of your cone. Because the disc has a certain amount of volume. If you use the density of water, you could compute the mass of the water within that disc. If you had the mass of the water in the disc, you just have to multiply by 9.8 to get the weight of the water. And then if you multiply by the distance that disc of water was lifted, you would then have mass times gravity times distance. You would end up having the work in joules associated with lifting that one disc of water. But now we don't want to know the mass, the joules of work associated with lifting one disc of water. We want to know the joules associated with lifting all the discs of water. And so the integral, if you integrated over where all of those discs lived, in this case between 0 and h, you would then sum up the work within each of those discs, which would be summing up the work across the entire tank. If you think about, there's one example that somebody asked about before yesterday's quiz, And it was the one about the triangles of area, right? And it was like, if you can come up with a figure that when you slice it, you get triangles, if you can compute the volume of one triangular slice, you just sum up over all the triangles and you get the volume, right? Your slices don't have to be discs or washers. You could also sum up volumes of triangles or triangular slices. You could also sum up amounts of work. There's nothing preventing you from doing that. In fact, that's exactly what we do today. So if you think of each sort of horizontal slice of water as its own slice of work, then you can imagine summing up all of those slices like a Riemann sum. Well, hey, if you took 592 slices instead of just a dozen, you're going to get an even better approximation. If you let number of slices go to infinity, the integral would give you the exact measure. And so that's really where the integral comes to the service of our computations. But now, to get an intuitive sense of how this works, imagine these two cones. Both of these cones have the same height and the same radius, albeit one of these cones is resting on its base and the other of these cones is resting on its point. Both of them have a spout that's of the exact same length on top. Now, if you think of the water within each of these cones as slices of water, and you conceptualize the relative weight of each of the slices and the relative distance of the lift associated with each of those slices, and then summing up the work accordingly, you can get a sense that one of these cones is going to encounter a lot more work to get the water out. So give it a thought. Chat up a neighbor. Give yourself a couple minutes to get your thoughts together, and then I'll see if anybody is willing to sponsor explanation for which tank is going to take more work and why. All right. Is anybody feeling brave enough to offer an explanation? Yeah, please. So the one on the left, that's right. Yes, the water at the bottom is going to have such a long distance. And so if you got this heavy stuff at the bottom, that's going to be so much distance on that heavy stuff. Whereas here at the bottom, you got light stuff. So if work is a function of distance, then heavy stuff, long distances, oh boy, like that's worst case scenario. And in fact, yeah, compared to these two examples, yes, there are still big slices on the one on the right, but at least they're close to the spout. So that's less work. Yeah, sweet. That's the intuition. But yet the intuition is, you're not just going to see these intuitive, like sort of true falsy type things. If we're going to get real precise and mathematical, right, we're going to use integrals. Integrals compute things exactly. So let's imagine a situation. Imagine you're walking in the woods, and imagine you run into a cliff. And well, before you fall over that cliff, you realize that there's a rope there, and that rope is 60 meters long. And incidentally, that rope has a linear density of 56 grams per meter. I actually went to a outdoors equipment website to verify this is a common linear density of a climbing rope. And now the question is, if you wanted to pull up that rope, how many joules to the joule would it take of work to pull up all the rope? Now, if you think about it, the rope at the top is being lifted a different distance than the rope at the bottom. So we're going to have to take all this into account. Wesley is going to walk us through the details of computing the joules exactly of lifting the. Okay. So here we go.
So I've drawn a little picture over here that kind of represents the situation we have. Here's our 60 meters of rope. And then I've also recorded the linear density, which is 56 grams per meter. So first off, all we know is that we want to calculate the work needed to pull up this rope. But the problem is that pulling up the rope is going to be harder when we start versus when we're almost done. It's going to be really easy. There's going to be almost no rope left. So it'll be really easy to pull up a little bit of rope versus to pull up a lot of rope. So in order to combat this problem, we are going to just consider a thin slice of our rope, which I've represented here by this dy, and you'll see why I use dy in a second. You can probably already guess it has something to do with integrals, but we will just consider this thin slice of rope so thin that we can say the work needed to compute this like little thin slice is just like one value for that one little thin slice. And that's going to be important. Then you can also see the bounds that I've put on here. I've said we're starting at y equals 0, and the end of our rope is y equals 60, which might seem a little backwards because our rope is going down. But you'll see that this, within context of the problem, actually makes sense. If you think about y equals 0 as being like, I have pulled up 0 meters of rope, and y equals 60 being the bottom of the rope that we have to pull up. That's just kind of a little to put this problem into perspective a little bit. And then down here, I've kind of got the layout for how we want to calculate work. We know that our work is going to be in the unit joules, and work is equal to force times distance. And then to get force, we need to have mass and acceleration, which we're just using gravity, which is 9.8 meters per second squared. And sometimes in these problems, we need to do a little bit of dimensional analysis. So as a reminder, I've put that a Newton is a kilogram times meters per second squared. And if you're paying attention, you might see why this is going to come up in a second. But let's get started calculating the work of one slice. Like I said, we're considering that really thin slice, and we're saying that little thin slice is dy meters in length. We're using dy because we're essentially talking about the change in y, which is like the change in our work needed to pull up the rope. And the amount, like I mentioned on the previous slide, the amount of work needed to pull up the rope is in flux. So that's why we consider such a thin little slice of dy meters. The mass, if you'll notice, I have changed from, we had the linear density of 56 grams per meter, but we want to make this in kilograms. So I've just divided 56 divided by 1,000, because there's 1,000 grams and 1 kilogram. So now we have 0.056 kilograms per meter. And remember, mass is just in kilograms or grams or whatever we're measuring in this case, kilograms. So we take the mass we take the linear density of the rope and we're multiplying it by our thin little slice, dy meters. And then those meters are going to cancel out. So we're left with a mass of rope. Next, once we have mass, we know we're looking for force, which is the same thing as weight. And so we need to multiply that mass of our slice times acceleration, in this case, gravity. So I do 0.056 dy times 9.8. And I like to keep all the numbers kind of laid out. I don't like to multiply them together. It helps me when I'm computing these problems to see, you know, what I've multiplied so far. Like I have mass, I have acceleration. What do I need now to calculate the work of a slice? I need distance. I say that my distance is y meters. You might be wondering why y meters? Going back to this picture might help us determine that. According to me, I've said I'm starting at y equals 0 and I'm going down to y equals 60 for my length of 60 meters of rope. This dy slice, this random slice I say is about Y meters down. I say that because the top is 0, the bottom is 60. So if I want to know how much work I need to pull up a slice that is 40 meters down, then that Y, that height would be 40. That makes sense. So that's Y. And we don't know where our slice is, so that's why we have to use a variable such as Y. Then once we have distance, we can calculate work because now we have force and distance. So we can calculate our work, which is shown here. And we know we did something right because our units are kilograms times meters squared per second squared, which is what 1 joule is. And now once we have the work of that one slice, we want to know the total work that it takes to pull up the entire rope. So that is when we integrate. So here's my formula that I found for one slice. And then the bounds for my definite integral are 0 to 60, which makes sense. That's coming from here, the rope, starting at 0, and I'm pulling up 60 meters of rope. So it's from 0 to 60. Then I can take out this constant. These are just constants. They pop out of the integral. And so now I have the integral of y dy, which looks very familiar. I can integrate that and get y squared over 2, evaluated from 0 to 60. And when I evaluate that, I get this 987.84 joules, which is the work needed to pull up the rope. Now, the last thing I want to mention is that I did it with y equals 0 and y equals 60, but you can say, you can reverse them as well. Say the top of the rope is y equals 60 and the bottom is y equals 0. And when we do that, all it changes is now the height of where our rope is, or sorry, where our slice is. For example, if I say this slice is again 40 meters down, then there would be 20 meters of rope left to pull up, which is what this would be calculating here. 60 minus 40 is 20. And when you do it the same with only changing the height of the slice, you get the same thing. And even if I said the top of the rope is 0 and the bottom is negative 60, you get the same thing again. So it just goes to show you, oh, but I should mention that when I do that, the height again changes to a negative y. So depending on where our bounds, or what we call the top of the rope and what we call the bottom of the rope, is going to affect the height of the slice. So that is very important. But maybe the point I'm trying to get at is that you can change these bounds and just make sure the height is in correspondence with what you have your bound set as. Although I do think it is the easiest to make your bound, to start at 0 and go to 60 in this case. But yes, hopefully that makes a little sense to calculate work. The process, remember, is right here. And remember that it can be helpful to use the dimensional analysis to kind of follow along and make sure you're calculating work correctly. But hopefully that helps.
Thank you, Wesley. Yeah, I like how Wesley pointed out the different coordinate systems. In some sense, it is up to you what coordinate system you choose. I do think the way Wesley did it as well initially makes a heck of a lot of sense. If you think of like where things are initially as y equals 0 or something, and then stemming down from there, yeah, it's a little bit weird to have y's go down to 60, but it actually makes a lot of sense because something at y equals 40 is lifted exactly 40 meters, and then the distance of your lift is exactly y, which makes the computation look kind of nice. When I saw Wesley do this morning for the 8 a.m. section, I was just morbidly curious, and I looked up how many kilocalories there are in a joule or vice versa, and 4,000 joules is 1 kilocalorie. So this was a quarter calorie burned, lifting up this little bit of rope. But interesting thoughts nonetheless. So to get some practice with these types of ideas, note in this example, we were not told the density of the chain, the linear density of the chain. However, if you have 80 kilograms of rope over 10 meters, if you run the numbers on that, that would be 8 kilograms per meter. So you'll need the computation 8 kilograms per meter, because if you're thinking of a little tiny piece of chain that is dy meters tall, you're going to need 8 kilograms per meter to figure out what the mass of that little tiny bit is. But nonetheless, here's a few manifestations of lifting a chain instead of pulling up a rope, but it's actually kind of similar to what Wes was looking at. So give yourself some time and harass a TA if you are at any step of the process, because there are a lot of thoughts that one could have related to this, or maybe not even sure, and you can help you sort it out. This is a lot of. All right, so let's touch base on these. So yeah, we want to try to use this idea of chopping up our chain into little tiny bits dy thin, because even if we chopped our chain into bits that were 1 meter long, the difference in the distance of the lift between the top and the bottom of a 1 meter chunk is non-negligible. And so we got to think of a really thin bit in order to sort this out. So the first one, we are lifting the chain 10 meters off the ground, effectively lifting the entire chain off the ground. The bottom of the chain as well, it's sort of still touching the ground. But now, if you think about the individual links of chain, right? Some links of chain have been lifted 10 meters. Other links of chain have only been lifted 6. Some have been lifted 4 meters. Others have been lifted practically nothing because they're still setting on the ground, just that bottom link, right? So we want to think of just a single link of the chain or something even narrower than that, like a dy meters bit of the chain. Because if we assume that we have a bit of chain that is only dy meters in height, then the difference in the distance from the ground to the top and the bottom is negligible. And we can just consider that to be y units up instead of like y units and then y plus some number of units to get to the top. So, right. Let's take it one bite at a time. So we've got dy meters of chain. We want to get this to figure out the force on this little bit of chain. So how are we going to get from length to force? Well, if we know there are 8 kilograms per meter, right? This is actually the density, the linear density of this chain. The density is going to allow us to go from meters to kilograms when we multiply by 8. So 8 dy is the number of kilograms of this tiny little slice of chain. But if 8 dy is the number of kilograms, multiplied by 9.8, now you have the newtons of that kilogram, the force of gravity on that little bit of chain. Now the next question is, if you know the force of gravity, we're doing work, force times distance. What is the distance that we have lifted that bit of chain? Well, it depends, doesn't it? If you lifted the chain to a height of 4, well, to y equals 4, you lifted it 4 units. If you lifted it to a height of y equals 8, you lifted it 8 units. In general, for any given y, the distance that we have lifted it is exactly y units. And so multiplying the force times the distance to get the work on any given slice of our chain, it is the dy times the 8 times the 9.8 times the y. That's the work on any given slice. But we don't want the work on any slice. We want the work on all the slices. So what are we going to do? We are going to integrate between all of the y's of interest. Now, y is the distance that we have lifted that bit of chain. And the minimum distance we've lifted a bit of chain is 0. The maximum distance we've lifted a bit of chain is 10. And so the domain for our variable y is going to be between 0 and 10. The 9.8 and the 8 come out. But by the way, we're done at this point if we just did the integral. But if you just are curious, there's the number of joules that pop out. But it only asks you to find the integral. On a quiz, you just have to find the integral, and then you'd be good. What about the second example? Now here we're only lifting one end to a height of 4, which means most of the chain is still sitting on the ground, no work being done. This is going to take a lot less work. And well, if we play it out here, it's still dy meters of chain. Density 8 kilograms per meter. So that's 8 dy kilograms in one little tiny bit of the chain. Multiply by 9.8, now you have 9.8 times 8 times dy newtons of force of gravity on that little tiny bit of chain. Once you know the force, you got to multiply by the distance. Well, what's the distance here? Well, it depends, right? If we were y equals 1 off the ground, we lifted 1 unit. If we were y equals 3 off the ground, we lifted 3. If we were y equals 4 off the ground, we lifted 4. For any given y, we would lift y units off the ground. Now, that gives us then multiplying the y times that 9.8 times 8 dy, the force times the distance, that's the work on any given slice of our chain. Y times 9.8 times 8 times dy. But now, where do we integrate? The y is the distance that we have lifted. And what is the minimum distance we lifted and the maximum distance we lifted? Well, the minimum distance we lifted was 0 because some of it's still sitting on the ground. The maximum distance we lifted was 4 because the highest it went was 4 meters off the ground. So integrating over all of those distances, 0 to 4, there we go. That's the integral. And there's our result. Here, look, by the way, we've lifted almost half the chain and it's way less than half the number of joules because lifting the second half is going to be so much more work because it's so much heavier. So it kind of makes sense if you really think about it physically. The last one, what if we're lifting the chain to 50 meters off the ground? Now, every link of chain is lifted at least 40 meters. No link of chain is lifted less than 40 meters. No link of chain is lifted more than 50 because the top of it's at 50. But really, all the cooking up at the beginning is the same. You've got dy meters for your little slice of chain. You multiply by 8 because that's linear density to get the number of kilograms in that little slice. You multiply by 9.8 now to have the force on that little slice. And then you multiply by the distance that you have lifted to get yourself the work on that slice. Once you got the work on the slice, what do? You integrate. You integrate to sum up all the works of all the slices. But now here, if y is the final height of your chain links, the final height of the chain links is between 40 and 50. So we got to be careful here. We're not integrating between 0 and 50 because none of our chain has a final height of 0. All of our chain has a final height between 40 and 50. And y is essentially playing the role of the final height of the chain. Note, by the way, this is different than in Wesley's example where y was the initial height of the rope. The rope was initially unraveled, whereas the chain is initially just lamely sitting on the ground. Where the y comes into play is when you look at the final snapshot of the picture. So y here is the final height of the rope. But nonetheless, yeah, integrate between 40 and 50. It's a huge number compared to the other. And yeah, 50 meters. There's probably only a few buildings in Knoxville that are 50 meters high, and we're lifting a huge 80-kilogram chain to the top. It's going to take a ton of work. So there we go. Yeah, kind of cool to think about. So where do we go from here? Here is a classic Calc 1 question. This is like, if there's a top 40 hits list of Calc 1 questions, pumping water from a tank and computing the work of it is on that top 40 list. Now, how are we going to compute the amount of work associated with pumping water from the tank? We are going to essentially think of bits, tiny bits of the water. Because if you imagine even 1 meter bit of the water in this tank, 1 meter tall, the difference in the distance of the lift from the top to the bottom of that 1 meter chunk of water is non-negligible. Whereas if you imagine a really thin slice of the water, the difference between the distance to the top and the bottom is negligible. And then you can consider that thin slice being lifted a fixed distance. But now, how could you even get to the point where you were computing the work on any of these slices? Well, if you had this tank, each slice of water is a disk, pi r squared dy. And then if you took pi r squared dy times the density of the water, now we're using a volumetric density, kilograms per meter cubed. But kilograms per meter cubed is such that if you multiply by a meter cubed, you get back a kilogram. So if you multiply by a volume, pi r squared dy meter cubed, you'll now multiply by 1,000, get the kilograms of the water in that slice. multiply by 9.8, you have the weight of the water, and then you could multiply by how far the water is lifted. Now, if you think about it here, if you use the convention that ground is y equals 0, we've used that in like every example, right? Res's example, where you initially were, y equals 0. The chain example, the ground is y equals 0. If you think of the ground as y equals 0 here, and then the top of the tank at y equals 5, please note, at the top of the tank, y equals 5, the distance of your lift is 0. At the bottom of the tank, y equals 0, the distance of your lift is 5. If you were 1 unit off the bottom, the distance of your lift is 4. How did you get the 4? You took the 5 minus the height. So 5 minus y is how far the lift went. And here we'd integrate between 0 to 5, assuming the tank was full. If the tank was only full 2 meters, we'd integrate between 0 and 2, because y here is the initial position of the water, not the final position. All the water finally is up at 5 meters because we pumped it out. But initially is where the water has interesting positions. Okay, nonetheless, let's see an example of this type of situation. Again, this is a classic, an oldie but a goodie. We've got this giant tank of water, right? 3 meters in radius, 5 meters in height. It's full of 4 meters of water. So some of the water is only being lifted a meter, some's being lifted 5. Boy, we're going to have to integrate and figure out how much work is required. Corey's going to help walk us through and see how we can compute the number of joules exactly of all this water.
Yes, I am. So we have this really scary looking question here. And the first thing that I do when I see something like this is I like to kind of boil down all of the important information and put it into a nice little pretty picture and get out every piece of information that I need, take away everything that I don't need because it's distracting to me when I'm trying to solve these problems. So here I kind of redrew our diagram, and you can tell that it's filled with water based on my beautiful picture of water inside it. We know that the water is filled up to a height of 4 meters, but the tank is 5 meters tall with this radius of 3 meters. And remember, we want to pump out all of the water in the tank. So we're going to use a method that's very similar to what we were just doing with the ropes and the chains. We're going to think about a really thin slice of water, and we're going to think about how much work it takes to pump out that slice of water from our tank. So I drew us a little slice of water here again, and it has this height of dy meters, which is just going to be getting really, really infinitely thin. But because we're in this nice cylindrical tank, we have the constant radius of 3 meters everywhere. So no matter what slice of water I'm looking at in my tank, it's always going to have this same shape. It's going to be dy meters tall, and it's going to have this radius of 3 meters because the radius of a cylinder is the same everywhere. That's pretty convenient here. So if we want to find the volume of this cylindrical slice that we're taking, all we have to do is use our volume of a cylinder formula because the slice is just a really thin cylinder. And that formula is volume equals pi r squared times h. But r squared, remember here, is just that constant of 3. And then the height is that dy. So the volume for any slice, no matter where we're looking in our tank, is always going to be the same pi times radius squared, which is 3 squared, times the height, which is dy. So that just comes out to 9 pi dy for any slice. So we're going to go ahead and use that. Remember that we just found volume, but if we're wanting to calculate the amount of work, we're going to need some idea about the mass of this slice. One thing that I didn't write down or that I use here, but that you might not have seen in the question was that they give us that water has a density of 1,000 kilograms per meter cubed. I certainly don't know that, but if that information is important on a problem like this, it should be given to you like it is in this question. So don't worry about that too much. Now we have the volume and we want to find the mass, and we're given the density, and there's this very convenient formula that tells us how density is related to mass and volume. So all we have to do is just rearrange this nice pretty formula into mass equals density times volume. We found the volume, we know the density, so that helps us just get this mass here. And if you want to check on those units, we get mass in kilograms is equal to kilograms per meter cubed times meters cubed. Those meters cubed are going to cancel out. We just get kilograms equal kilograms. That's a good sign. We haven't messed up so far. So we know that the density of water here is 1,000 kilograms per meter cubed. We're multiplying that by our volume of the slice, which is going to be, again, meters cubed, because we're looking at a dy meters tall height, and then a 3 meters long radius, if you want to say. So we have this 1,000 kilograms per meter cubed density times this 9 pi dy meters cubed volume of our slice. And that's going to tell us that the mass, again, for every slice, because it doesn't matter where we're looking because our volume is always the same. The density doesn't change where we're looking on our in our water. So this mass is always going to be 9 pi times 1000 dy kilograms. And that's great because kilograms are the units that are going to come out in our newtons, which we're going to find here again by just using that force of gravity, 9.8 meters per second squared. So that's going to give us kilograms times meters over second squared, which is just a newton. Again, we just have force equal to mass times acceleration. We're using that mass of every slice that we just found up here, 9 pi times 1000 dy, and we're multiplying it by acceleration from gravity. So that's just 9,000 pi times 9.8 dy. All you have to do is multiply all that stuff that we just found. And again, this is our units, kilogram meters per second squared, which is the same thing as a newton. So the last thing that we have to find out, remember we're wanting to find work, but now all we know is the force. We need to find out how much each slice is being lifted or how much distance each slice has to travel as we're pumping it out of the tank. So that's what we're going to do here. This is where we should be expecting some type of variable. So we're expecting a y to pop up, because if I'm looking at a slice at the top here, like slice 1, well, I only have to pump that out 1 meter. Let's say it's at the top at the 4 meters. If I pump that slice 1 meter up, it's going to be at 5 meters. So it's going to be out of the tank. That's great. I'm done with that slice. I don't have to worry about it anymore. But if I take slice 2, which is down here, definitely not at the top of our 4 meters, and I pump that up by 1 meter, it's definitely not going to be out of the tank. So I can't just forget about it. I have to pump it up more distance. So that's what we're going to be using here. Please forgive my bad labeling scheme. This is a different dy than the dy from integrals. I was using it d like distance depending on y, but we can pretend that that's not a big issue here. We can just think about that as its own thing, as just a distance. But if we're looking at some height on our tank and our slice of water at some height y, well, whatever distance we pump out, when we add that to our initial height, we're going to go up this distance that we're pumping it out. We need to be at the top of our tank, which is 5 meters tall. So we need to have our starting distance or our starting height of y plus our distance that we're pumping that slice out needs to give us 5, which is this equation right here. And these are all in meters, so that's really nice. So we can just rearrange that equation to find that the distance we're pumping out each slice is just 5 minus y. So pretty good. Now we know our distance. We already found our force for every slice. So all we have to do is remember that work is equal to force times distance, and we can find the work needed for any particular slice. It's just this distance times this force that we found for each slice. And because our water in the tank starts at 0 meters from the bottom and ends at 4 meters from the bottom, or 4 meters tall, if you want to think about that, then we're integrating over the interval 0 to 4, because remember this y is our starting height. So we take our integral over 0 to 4, and we're just integrating the work of each slice for any of those heights y in that interval. And know that the work for any slice is given by this equation, this 9,000 pi times 9.8 dy, that was our force, and times the 5 minus y, which is our distance. I mean, technically this is done, but we really like to have our dy at the end, so I kind of rearranged this integral, and we have integral from 0 to 4 of 9.8 times 9,000 pi times 5 minus y, all dy. I didn't go any further with this and give you a final answer because the question just said to find an integral that would evaluate to the work required, and I didn't want to calculate all of that out. But if you wanted to, you definitely could, but that would be how to set up your integral, and now we found it, so that's great. That was like a lot really fast. So anyone have any questions? Okay, great.
Before I walk sort of back to the front, I just wanted to point out this board here. One of the co-instructors from the 3 p.m. section even was just sort of ruminating a thought after seeing all these examples today. It was like, he was like, hey, yo, Mark, I'm pretty sure this is what happens in every one of these examples. You essentially are computing the force associated with your dy, and then you're multiplying by f of y, where f is some function that is the distance that the dy was lifted. And yeah, that totally comes into play here, right? Because the force is the 9.8 times 9,000 pi times dy. That's the force associated with the dy. And then the 5 minus y is the distance that was lifted. And then as far as the bounds go, the bounds are always associated with the minimum and maximum values of your y. And in this case, if you think of the Y as the initial height of the water, right? So starting height Y, right? If starting height is Y, the starting height goes between 0 and 4. And then, boy, that just feels very right. So I've never actually taken the time to conceptualize it precisely in that way, even though I've thought of it so many times, I guess never communicated it in that way. So right, it's a lot of words. Well, given the time here, focus on the first one. Give yourself 3 or 4 minutes. See if you can't even begin to conceptualize what's going on here with this first one. We got a rectangular tank. There's only 2 meters of water in it, but it's 6 meters tall. Think about a slice of water, a thin one. What's the volume of that? What's the mass of that stuff? What's the weight of that stuff? How far is that slice moving? The abruptness of this pause, but check it out. If you think of a thin slice of water, that slice of water is living between y equals 0 and y equals 2. If you were at y equals 0, you're lifting 6. If you're at y equals 1, you're lifting 5. So the distance that slice of water is lifted is 6 minus y. Okay, so we know the distance, but now what's the force of that slice? Well, the volume is definitely 4 by 3 by dy. Multiply that volume by 1,000, the kilograms per meter. Now you have a mass. Multiply by 9.8. Now you just went from kilograms to newtons. That's the force of your slice. Take the force of your slice times 6 minus y, the distance of your slice. You have the work of your slice. You want to sum up all the slices, integrate between the minimum and the maximum values of y here, which relevant in this situation is y equals 0 and y equals 2. It's a huge number of joules because it's a big tank. If you take a look at the second example on your own time, there's a conical tank, that type of similar triangle thing, which will make you flash back to some exercises from Calc 1, is something that'll show up in your WebAssign. So that'll be a nice reference for you when you get to that. Speaking of WebAssign, don't forget the volumes WebAssign is due tomorrow. You also got a work WebAssign due Sunday. This is a rough homework week in this class, I must say. We fortunately get our feet on the ground on Friday with like a more down-to-earth topic.